concentrates on the science of physics. And I'll be clear about my bias about physics. It is, in some ways, the fundamental science because it's the simplest science. Now, I know some of you have had experiences that might lead you to believe otherwise, but it deals with the simplest systems and like particles, atoms, moons, Earths, galaxies. Chemistry has to deal with horribly complex systems of particles. If you add the element of life to get to biology, then it just escapes the realm of science altogether to some extent. And heaven forbid, if you add the element of brain to that life to talk about psychology, then you're in really deep weeds. So we're going to talk about some simple science and the people who have created it. And today it's Isaac Newton. Last time we talked about the contributions of Galileo particularly. Galileo died in the summer of 1642, and Newton was born on Christmas Day in 1642. So we're going to concentrate on him and a couple of people who played an important role, not in his, well, one of them in his life, the other one in his physics. So let me see if I can make this advance. Did it? Okay. This is just an overview of some important dates in Newton's life, and I'll come back and say more about elements of this. As I said, he was born on Christmas Day in 1642. He was born in a fairly modest home to a working class family who was sufficiently wealthy to own a farm. He entered Trinity College at Cambridge in 1661, a couple of years older perhaps than most students who were going off to university in those days. After being there for a couple of years, the plague forced the university to close down, and he went back to the family farm and during that next 2 years studied light, motion, gravity, and invented differential and integral calculus, among other things. And I'll say more about those 2 years in a moment. His first publication was a publication on the mathematical topic of infinite series of numbers, and I'll say more about that too. In 1672, he invented a new type of telescope. I got these dates out of one. In 1669, he became Lucasian Chair of Mathematics at Cambridge. Significant visit from Edmund Halley in 84. And in 87, publication of Principia Mathematica, which most people would regard as the most important science book ever written, with perhaps some debate about Darwin's books in that debate. By 1696, he essentially left science, became Warden of the Royal Mint and then Master of the Royal Mint, published a book on optics later, and was knighted, died in 1727. So that's the time period we're talking about. Now I'll say a little bit more about various aspects of this in the next few minutes, and I will refer to notes from time to time. His father died 3 months before he was born, and Newton was a very sickly child. He was premature. Apparently, according to his uncle, he was small enough to fit into a quart jar when he came home, and he was not given any real chance at living. But he did, and of course, as is the case with many premature children, he was sickly throughout his childhood. He was not an outdoor person particularly, nor was he an athlete of any kind. When he was 3, his mother remarried a wealthy clergyman and moved away, left him in the care of his grandmother. And so his grandmother essentially raised him for several years, and his parents, his mother and his stepfather, lived in a village not too far away. The stepfather died, and his mother came home after 8 years with 3 small children who were half-siblings to Newton. And a couple of years later, he was old enough to go away to school. So just real quickly in terms of visual imaging, this will move. Let's try this. Whoa. Yeah, this is not really behaving the way I expect it to. Well, we'll just go on and I'll try to figure out what is not happening properly in this. All right, now let's go back there. Let's go up to slideshow. Let's do it. Let's go up here to slideshow so we get the full screen. There we go. All right. And let's go over here to, yeah. All right. First slide. Okay, we're good. Thank you. Okay, this is Woolsthorpe Manor, Newton's birthplace. It's still in existence. It's described as a typical yeoman's farmhouse of the period. It looks like a pretty substantial house to me, but it's not the house of a wealthy person. And when he was a little bit older, he was sent off to, well, again, still does not want to. There we go. This is just another painting of Woolsthorpe Manor, and according to the artist, the tree on the left background is an apple tree, for whatever significance that might have to you. This is Grantham Free School, where he was sent away essentially to do what I would consider high school, middle and high school work. He had been tutored a little bit privately at home, mostly financed by an uncle who sort of took an interest in him. At this school, he lodged with the schoolmaster, and that same uncle convinced the mother Newton's mother, that he was not going to be a farmer, so it was agreed that he would enroll in Cambridge. What? This thing doesn't, okay, we'll go this way. This is Trinity College in Cambridge, where he enrolled as a young man in 1661. Now, he was not wealthy, as I said, so he went to Cambridge as what they call a sizar. I guess I pronounced that right, and perhaps after we're finished, Dr. Potter can tell us a little bit about what life was like at Cambridge and Oxford in the 18th, 17th, and 18th centuries. But that meant that he was paid to be a servant to other students, so that he would have tuition, room and board at Cambridge, or at least room and board. Maybe his uncle paid tuition. It's not really clear. But he worked anyway as a sizar and as a tutor, intending to study law. But Cambridge was very much in the Aristotelian philosophical sphere at this time. So in addition to studying Aristotle and Aristotle's philosophy, he also would have read Galileo, Kepler. He would have read Descartes and other scientists who were thinking about some of the same issues that Newton came to think about. and he switched to study of mathematics. Now that's very curious because he showed no proclivity whatever for mathematics as at the Grantham Free School, nor did he have any particular interest in mathematics when he began at Cambridge. But he came under the influence of a man named Isaac Barrow, who was a mathematician of some repute and who was the holder of the chair, the Lucasian chair of mathematics at the time. And Barrow gave him a copy of Euclid's Elements, which Newton found very confusing at first. Now, for those of you who haven't read Euclid's Elements, and that includes me, you've all had some introduction to plane geometry somewhere in your high school careers, unlike modern students who rarely see anything about plane geometry. You've had the opportunity to think about how you construct proofs and reason logically. That confounded Newton for some time. And at first he thought that it was impossible. Then he thought that some of it was too trivial. And then he spent really some time thinking about it and mastered both plane geometry and geometry and began to think more seriously about mathematics. In 1664, he became a fellow or a scholar, which guaranteed him 4 years of financial support at Cambridge. And anyway, he wrote about his time away from Cambridge during the plague and said that during that time he first understood the theory of gravitation, and we'll talk about that a little bit more, and the theory of optics. He was the first person to realize that white light is made up of the colors of the rainbow, and much mathematics, both integral and differential calculus and infinite series. Now, unlike most of the scientists we know, Newton was very reluctant to publish any of his work. Only published it when somebody appeared to be publishing something that would have given them preeminence in terms of the discovery. So if somebody was about to publish something on infinite series, he was going to publish first on infinite series, and the same thing is true with calculus when he eventually do it. He was afraid that somebody else would get credit for something he had found earlier. Now, here's a curious part about this, and many people realize it, but when he got back to Cambridge in 1668, he published his little book, or wrote his little book on dealing with infinite series, and then began to do research in alchemy. Unless you're a mathematician, when I say infinite series, you don't respond to what I'm talking about. Is that a fair statement? Well, you can think about a series of numbers like 1 plus 2 plus 3 plus 4 plus 5, stretching out as many numbers as you can imagine. That's an infinite series. And that particular infinite series is boundless. Obviously, you can always add another number to it and make it larger. It has no limit. But what about a series like 1 plus a half plus a third plus a fourth plus a fifth? Is there some possibility that at some point those fractions become so small that they're not adding anything to it, that number, that series actually has a sum? And that was something that was novel, and yet it became central to a problem that Newton had to solve in terms of gravity. I'll talk about that more later. But he worked out ways of dealing with that, of answering the questions of whether or not the series had a sum and how you could calculate that sum. And his book actually also referred to some issues, some parts of his invention of calculus. Because if you've ever taken a calculus course, you know that the symbol for integration looks like a long, tall S, which stands for sum. And an integral is essentially a sum done in a fancy way. So he had, in his own mind, by this point in his career, done all the physics he intended to do and had moved into the study of alchemy. Now, alchemy is is it fair to say a predecessor of chemistry, Neil? It's people playing around with chemicals and trying to understand what makes things work the way they do. And many of them were looking for what was called the philosopher's stone, something that would turn lead into gold. And Newton has notes in his journals about the philosopher's stone. And when Newton died, most of the work that he had done in alchemy was boxed up in his papers and stored. And nobody looked at it until very recently. Within the last 20 years or so, some chemists have begun to examine Newton's work carefully, and they've discovered that he was very close to some pieces of discovery that would have led right into modern chemistry. It wasn't all the kind of thing that you might have thought about if you'd seen a movie about alchemy and people just pouring stuff willy-nilly into test tubes to see what happened. It was much more disciplined than that. But it was not the physics for which he was known. He wrote this paper on infinite series and showed it to Barrow, his mentor. And Barrow sent it off to another mathematician in London to be evaluated because he didn't think that he was capable of evaluating it fairly. The mathematician wanted immediately to know who had written it, and because he wanted to present it to the Royal Society of London as an academic paper. And that's the point at which Newton was sort of forced to write his book and get it, even though it wasn't published until much later. He actually wrote it at this point, and it was presented to the Royal Academy. And I'll say more about the Royal Society in a little bit. His first major public invention was a telescope. And let's go forward a little bit. That's a painting from the Royal Society collection of Newton at his desk. And if you look really carefully at that robe's a whole lot fancier than any academic robe I ever wore. I mentioned before the work on optics. His book on optics, which wasn't published until fairly late in his scientific career, speculated a great deal on the nature of light. According to Aristotle and thus to the teachings of the Catholic Church, the light that comes from the sun is what was called pure light. And because it was pure light, it could not be broken up. Newton showed with a prism that you could disperse it into various colors. Not only did he do that, but he also understood why. He studied refraction, which is the bending of light as it moves from one material into another. Wrote ways of forecasting how much it bent, and found that the different colors were refracted by different amounts, which is why you get the separation when it comes through here. Red is not bent so severely as blue. And not only could he do that, but he could also pass those colors through another prism and get back to the white or pure light. He hypothesized or thought about what light might be. Is it in the nature of particles, which he called corpuscles? Certainly light tends to look like it's traveling in a straight line path, and that's one of the reasons you have shadows. Or is it a wave phenomenon? He could understand it on both, and basically came down with a guess that it was a series of particles. And in a subsequent lecture, we'll talk about why that guess was found to be wrong, or right, because it's both, but I won't go there yet. Anyway, he also studied the reflection of light from mirror surfaces and realized that you could make a mirror that was, if it's not flat or plane, if it were convex, you could make a mirror reflect light outward, which is what happens when you look at the passenger side rear view mirror on your car. You get an image that is bigger and in which things look smaller than they actually are, or closer than they are, or more distant than they actually are. Or you could make a mirror that was concave, that is shaped inward, and it would focus light. And once he saw that he could focus light with a mirror, he decided he could make a telescope with a mirror, because the ability of lenses to bring lights to focus is what makes the telescope or eyeglasses or any of these things work. So he invented a new kind of telescope, which revolutionized astronomy. Edmund Halley, whom I mentioned briefly, came to Oxford as a student and brought with him a telescope that his father had purchased, which was 20 feet long. And that was necessary in order to get the size and the focal lengths in order to really get the magnification he wanted. You could get that magnification easily with a telescope that's 3 feet long and a mirror. So that was the Newtonian telescope is the primary form of telescope that you find today in terms of optical telescopes. But think about building this thing. Newton could not go down to the corner store and buy a mirror that was curved. He had to make it himself. Not only that, he had to make the tools for constructing the mirror and everything else himself. So this is a different era of doing science, and this is Newton's telescope, which is in the Royal Society collection in London. And it's a very finely crafted instrument, made out of brass, all built by hand by Isaac Newton. And this telescope was sufficient to guarantee his invitation to join the Royal Society of London. Now, I mentioned the Royal Society, and again, that's something that not most of you are familiar with. The Royal Society of London was formed in, about 1663, about the time the plague was hitting London. And two of the major founders were Christopher Wren, whom some of you know as an architect both in this country and in England, and Robert Boyle. And again, many of you have studied Boyle's Law somewhere in your high school science courses, dealing with pressures and gases, and several others who met to hear lectures among themselves and incorporated themselves into the Royal Society of London for essentially the expansion of knowledge. It has become arguably the most prestigious science academy in the world over the years. And almost any scientist of any repute that you can name has been a member of the Royal Society, whether it's Darwin or Newton or Maxwell or Einstein or Hawking. They've all been members of the Royal Society over the years. So for a young man who's not yet 25 years old to be invited to join the Royal Society, that's really quite an accomplishment. And it was sort of a mixed experience for Newton, as I'll try to explain. Anyway, in the 1670s, Newton began to study theology. He learned Hebrew and became a serious theologian. And there are still theologians today who read some of his work in the area of theology. He was not happy with the current beliefs of the Church of England, and that's unfortunate because he was required as a fellow of Trinity College to take holy orders. But fortunately, the Church of England was more flexible than Galileo had found the Catholic Church in these matters. And King Charles II issued a royal decree excusing Newton from the necessity of taking holy orders. The decree specified that in perpetuity the Lucasian professor need not take holy orders. Now, I missed saying something in the middle of all that. In 1669, I think, Isaac Barrow resigned the Lucasian chair and recommended that Newton become the Lucasian chair of mathematics at Trinity College, Cambridge. The Lucasian chair of mathematics has been held by such people as Newton, and he's the second person. Barrow was the first. Many names that physicists would recognize quickly, people like Stokes and Larmor and Airy, Paul Dirac, who was a major founder of quantum theory, held the chair. And most recently, Stephen Hawking was Lucasian chair of mathematics from 1941 until 2018, roughly. I think Michael Cates is the current chair of Lucasian chair of mathematics. Charles Babbage is another one, essentially the inventor of the computer, who held the Lucasian chair of mathematics. Again, Cambridge will tell you that is the most prestigious academic chair in the world. Whether or not it is I don't know how you measure it, but Cambridge would certainly say that. Anyway, the Lucasian chair did not have to take holy orders. So let's get to Newton's physics just a little bit. In 1684, there was an argument at the Royal Society among three people: Sir Christopher Wren, Edmund Halley, and Robert Hooke. More about the argument in a moment. This, by the way, is Newton's window at Cambridge. It's the window into his living quarters when he was a faculty member there. And that is an apple tree also outside the thing. Edmund Halley, I actually put a separate slide in about him, is a very important astronomer. He became a member of the Queen's College at Oxford in 1673 at a very young age. And in 1675, at the age of 19, he wrote a letter to John Flamsteed, who was the royal astronomer, and talked about some errors he had found in the charts of planetary positions, both from Kepler and from people building on Kepler's work. And Flamsteed encouraged him to publish it. So he published it, and then he dropped out of Oxford and moved to St. Helena to map the southern skies, to do an astronomical or star map of the southern skies, which were pretty much virgin territory for astronomers, since most of them were from the northern hemisphere. He spent 3 years there and returned to Oxford. By then, his residency at Oxford had expired, and Oxford refused to give him a bachelor's degree. But as I guess was not unusual in those days, the King Charles in this case, interceded and said to Oxford, give him a degree. So he was given a master's degree, and he became a member of the Royal Society. He then began to study comet orbits, and he was particularly interested in a comet that seems to have had a period of 75 years. We know that as Halley's Comet. But he was concerned about the orbit of that comet, and that's what the argument was about. Hooke and Halley and Christopher Wren were arguing over whether or not a comet orbit and thus the planets themselves had motions that could result from a gravitational force that varied inversely with the distance between them, and actually inversely as a square of the distance between them. And Hooke claimed that he had discovered this a long time ago, and that had to be that way, and Wren had another view, and Halley had yet another view. So Halley wrote in his notes the following. Mr. Hooke said that he had it, but that he would conceal it for some time so that others trying and failing might know how to value it when he should make it public. Robert Hooke had an interesting way of doing things. He would make conjectures, and he would put them sometimes into a public, coded or a public form, so that if somebody came along and proved that to be true, he could say, well, I had it back here, I just didn't tell you. If you just read this right, you can see it. And there is a law called Hooke's Law that has to do with the fact that as you stretch a spring or a rubber band or anything else, the further you stretch it, the harder you have to pull on it to stretch it further. That's basically called Hooke's Law. And he actually had a little Latin puzzle saying that that's what it was, and he never published it until somebody else tried to claim that they had discovered that. Well, anyway, one of them in that suggested that Newton had been working on this in his youth and maybe could answer the question. So Halley went up to Cambridge from Oxford and talked to Newton about the orbit of this comet and planets. And Newton said, oh yeah, he said, I worked that out quite a while ago. It's right over here. And he started shuffling through his papers and said, well, I can't really find it, but if you give me a little bit of time, I'll send it to you. So a few weeks later, Halley got this document from Newton where he had clearly worked out the fact that if the force between planets goes as the inverse square of the distance, then the orbit would be elliptical, and vice versa. If the planet's orbit is elliptical, then the force has to be an inverse square force. And Halley was really impressed by this, and so he went back to Newton and said, you know, you really have to publish this. And Newton resisted, and Halley eventually said, I'll pay for it. So Newton wrote this book, which, as I said, was perhaps the most important science book ever written, the Principia Mathematica, and 2 years later it was published at Edmund Halley's expense. There's a copy of part of the title page and the original on the right, and then an English translation on the left. The original was written in Latin, which causes some problems in translation. But this book, which is very difficult to read, at least to read the scientific part of it, almost overnight became a sensation and began to change the way people thought about both the world and science. And a little bit more about that in a minute. Its importance was appreciated by the scientific community almost immediately. And Newton became a very public figure at that point. And as I said, he left Cambridge for London, where he's appointed eventually Master of the Royal Mint. Now, he was you might think he was just sort of putting himself out to pasture when he accepted this gravy government job. But we have an expert on English coinage here and history of coinage, and he was definitely anything but a pacifist in terms of taking over this job. One of the big problems with English currency was the fact that one that was often counterfeited, and two, that the coinage was always being robbed by people shaving off the edges of it so they could deposit a little extra silver and a little extra silver. So one of the things that Newton did was to cause the coins to be milled. That's the little raised edge around the outside, which is very difficult to duplicate, and it almost overnight stopped the practice of carving. He was also a very energetic prosecutor of people who transgressed. They paid the price, the full price allowed by law, if they were caught during his time as a public servant. And he was admired, I think, almost universally for the work he did as a public servant. He was knighted by Queen Anne, as I said, and he continued to argue with especially Robert Hooke about who discovered had the credit for discovering the connection between elliptical orbits and the inverse square law. And he argued a lot with Gottfried Leibniz, a German mathematician, who pretty much invented calculus independently from Newton. Actually, Newton's was prior. The difference is that Leibniz, as a mathematician, intending this to be something that added to the canon of mathematics, was very careful about his proofs of the assertions that he made. Newton invented calculus as a shortcut. In other words, he looked at the calculations that were necessary to establish the relationships that I'm talking about. And the tools that he had, the scholarly tools that he had, were trigonometry and plane geometry. And he recognized how hard it was going to be to construct a plane geometry proof of this assertion. So he invented calculus to convince himself that it was true before he went to the trouble of doing the plane geometry. And the plane geometry and the Principia for just this one thing is like 20 pages of proofs. And if you ever remember doing those proofs, the ones you did in high school were long if they took more than a page of writing down your theorems and so forth. So it's for Newton, it was a mathematical shortcut, a tool, as mathematics often is in the physics community. And for Leibniz, it was central to everything he did. But it's pretty clear that Newton's calculus came well before Leibniz. Now, a little bit of physics. Newton, well, before I get to that, let me share just a couple of other things with you that I print out as a precursor to this. Newton made some assertions in the preface of his book. And two of those assertions are things that we sort of take for granted. But if you think about it for a moment, maybe you shouldn't. What is time? Tough question, isn't it? We use it every day. Use the concept every day. But what is it? And the corollary, the other piece is, what is space? Physics, the motion involves things moving from one point to another through space over time. All right? So Newton says, absolute, true, and mathematical time of itself and from its own nature flows equably without regard to anything external, and by another name is called duration. All right? Does that clarify things for you? In other words, he didn't have any better understanding of time than we do. Absolute space in its own nature, without regard to anything external, remains always similar and immovable. Now, that's a little bit easier to envision, because what he's saying is that there is such a thing as absolute space, and that therefore there's such a thing as absolute position in that space. So if I ask, where are we? right now, I could elicit hundreds of different answers from you. Relative to what? Relative to the city of Lynchburg, relative to Westminster Canterbury's complex, relative to the state of Virginia, relative to the earth. Where's the earth? 93 million miles roughly from a star that it's orbiting about. And that whole solar system is three-quarters of the way out the one arm of a galaxy called the Milky Way. And you go on and on and on. So where are we? Well, according to Newton, there was a theoretical answer to that. There was this, somehow you can imagine some sort of fixed coordinate system in space that it was absolute. Up, down, left, right, front, back, and relative to that coordinate system, you could fix your position. That's what absolute space meant to Newton. Now, as we get to Einstein, if those of you who might be here when we get to that talk, you'll find that Einstein had a very different concept, or developed a very different concept. But that's Newtonian space and time. Time flows. It's independent of where we are. It has nothing to do with where we are. And yet for modern physics, those two are inextricably entwined with one another, space and time, in a way that you can't separate them. So that's one thing that Newton talked about in the sort of first third of the Principia. Another thing, is what he called rules for reasoning, and I just want to talk about one of them. We are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. In other words, true, meaning that everybody believes that to be the case, and sufficient, not something where you have to keep adding things. And in some ways, this is a restatement of a philosophical principle called Occam's razor. If you have multiple theories that explain the same thing, the one that has the fewest assumptions is the one that's going to be chosen. And so Newton actually this is his philosophical background creeping into the beginning of this book. And of course, it's a book of natural philosophy. There was no physics. That field didn't exist prior to Newton. But anyway, as he moves in to discuss motion, he wrote what he called, he didn't call them laws. Okay, other people have attached the term law to them, but this is the way they're presented pretty much in a modern science textbook. The first one is a restatement of basically what Galileo determined, and that is that all objects have inertia. Now, you have to define what inertia is. Inertia is essentially a resistance to being to any kind of change in its state of motion. If you have an object like let's think about the Earth. It requires an enormous force to keep the Earth moving as it's moving around the sun. I once did a calculation of the size of a cable that would be required to provide the force that keeps the moon moving around the Earth. And made out of the most modern materials, that cable would have a diameter that was larger than the diameter of the Earth in order to provide the tensile strength to pull the moon towards the Earth as gravity does. Now, the other way this first law is often stated is objects at rest remain at rest, objects in motion remain in motion unless acted upon by a force. Just a total, as we said in the last lecture, total reversal of Aristotle's notion of the way motion occurs. Now, Betsy Smith sent me a very nice article from the Cardinal published yesterday or so on a philosopher at Virginia Tech who is quibbling with the translation of this first law, the word unless. because he says he's concerned that it might imply that there's some place in the earth or some place in the universe where there are no forces. And everywhere in the universe is subject to the force of gravity. So that's not what Newton meant, and that's the way it got translated. So he's looking at a little bit more subtle translation. Well, all of these laws are getting looked at very closely by people, have been over the years, and sometimes they are not immutable. But this is the way people think about it. The second law, many people think it's that the first law is unnecessary with the second law. Says that if you want to change the state of motion, you have to apply a force. If you want to slow something down, speed it up, make it move in a circle, you have to apply some kind of force. It doesn't just happen. And if you don't apply a force, it's just going to keep on going. But there's much more to it than that. The way it's often stated, I stated it the inverse way, but the way it's mostly written is that force equals mass times acceleration. If you imagine that you have a Volkswagen Beetle from the 60s and it runs out of gas, you can imagine putting it in neutral and pushing it. And most people can move, on flat ground at least, a Volkswagen Beetle pretty easily. But if it's a 1982 Ford Explorer, you can put it in neutral and you can push all you want, and it's not going to move. And that's because you can't apply enough force to make it move. If you put two people behind the Volkswagen, you can make it accelerate twice as fast. This is a very simple principle in appearance. I hesitate to even mention this, but I think it's important to really understand the scope of Newton's work. This force equals mass times acceleration is really what mathematicians would call a differential equation. Buried in this, in the modern term, are derivatives, which are part of something that came out of Newton's calculus. Because the acceleration is the rate of change of velocity, and velocity is the rate of change of time. Now, when you solve an algebraic equation, and I know you all do this every day, one that says 3x equals 7, you're looking for a value of x, a number, such that when you substitute it for x, you get 7. 3 times that number is 7. In other words, the solution to the algebraic equation is a number. And you could sit and guess the number without ever going through any kind of formal structure. I have a son who's very good at doing that. He couldn't tell you how he got the number, but he could get it just like that, just pretty much by trial and error. This equation is really different because when you solve it, you don't have an equation, you have a relationship, what we call a mathematical function. And what that means is that if I know the force that acts on something, I can calculate its acceleration, and from the acceleration I can calculate its speed, and I can calculate where it goes, and I can tell you where it's going to be at any time in the future. This is the first thing that appears in modern science where there is a strict predictability. If you tell me the force, then I can tell you how it's going to move pretty much forever. That's power. And that's power that was not totally implicit in what Newton wrote. It was explicit in what Newton wrote. It was implicit in what Newton wrote. But this is the key piece of this. Now, this is the third one, and again, you all know that. You may not appreciate it, but for every force, there's an equal and opposite reaction force. If it weren't true, you wouldn't be able to move. How do you walk? You push back on the floor pushes you forward. If you don't believe that, try it on ice. Push back all you want. You're not going to go forward. You might go down, but you're not going to go forward. So it is a very simple looking rule, but again, a very important piece of understanding motion. That's enough of that. All right. So let's talk about gravity. This is, I tried to reproduce Newton's original. I couldn't get enough contrast from the copy that I had, but this is a classroom version of his original drawing. Let's think about an object that is falling. And the apocryphal story is that he got this idea from sitting under an apple tree and watching an apple fall. If you imagine going to the top of a high mountain and firing a cannon, the cannonball is just going to go and hit over here somewhere. Now that may be greatly exaggerated, but that's what it's going to do. It's going to fall to earth, right? But if you fire it faster, it's still going to fall to earth, and it's going to hit somewhere else. Can you imagine it firing it fast enough so that it continues to fall but never gets any closer to the Earth's surface because of the curvature of the Earth? That's the reasoning that Newton used to link gravity, whatever gravity is, to orbits. And again, for a physics student, it's a very simple kind of calculation to carry out. It's probably in chapter 4 or 5 of every freshman physics book in the country. If you fire it too fast, then it's not going to fall fast enough to complete the orbit, or it's going to make a very long elliptical orbit and come back, depending on just how fast that is. Now, Newton was even shrewder than that. He said, okay, let's imagine that he's thinking about the apple falling. The apple falls, and you know that Galileo had to build an inclined plane to slow down that fall so that he could measure the relationship between how far it fell and how long it took to fall. So he had a sense of what we would call the acceleration due to gravity here on the surface of the Earth. Suppose that this, you're looking at the Earth, and this orbit out here is the orbit of the Moon. If there were no gravity, it would go in a straight line path according to the first law. So if you think about a little geometry, say it would have gone out here in the first minute, and it should have been down here. You can figure out how far it fell during that minute, how far it would have to fall in order to be in orbit. And so Newton actually calculated the acceleration of the Moon relative to the Earth and showed to himself that it was in the same relationship as 1 over the distance squared. In other words, he calculated what the acceleration of the Moon would be in order to make an orbit rather than keep going straight. Very clever calculation. Very clever man. Well, that resulted in, whoops, I can't go back. Okay. It went too far forward. That resulted in universal law of gravity, which says that every particle of matter in the universe attracts every other particle, and that the force is dependent on the product of the two masses and inversely dependent on the distance between them squared. That is a relationship that guarantees the elliptical orbit that Kepler found. He immediately saw as a corollary to that Kepler's laws were true. In other words, Kepler's laws were empirical, based purely on data, no understanding of why. Newton said, I know why, and I can show you. And that's part of the power of the Principia. All that's buried in the Principia Mathematica. But it would have remained buried, perhaps, for a while, had it not been for this person. And I skipped 2 slides, one of her and one of her lover, who is perhaps well known to all of you anyway. This is Gabrielle Amélie Letonellier de Breteuil, the Marquise de Châtelet. Now, how many of you have heard of Emily? I'm sure some of you have. You should have if you haven't, which is why I'm talking about her. Let's start with Voltaire. You all have undoubtedly read something by Voltaire in your lives, or at least know something about Voltaire. Voltaire was a very ardent proponent of free speech, a very ardent advocate, opponent to certain religious beliefs, often imprisoned for his outrageous remarks. But Voltaire was also a polymath of some significance, and he read everything. And he read Newton's Principia and was impressed with it. He was not a mathematician, but he mastered what he needed to do to understand it. This lady, just a little bit about background about her. Actually worked with Voltaire to translate the Principia into French. Voltaire published shall I say, abridged translation of the Principia, and actually acknowledged in the frontispiece that Émilie de Châtelet had done all of the translation and some editing, but did not give her co-authorship. This is the inner frontispiece of Voltaire's translation, and that's Voltaire on the bottom, and those are his muses for this book, Newton and Émilie de Châtelet. And I don't know who did the etching; it's uncredited, but that's the drawing. Voltaire wrote a letter to King Frederick of Prussia extolling Émilie de Châtelet, and said that she was a great man whose only fault was being a woman. She was born into one of 6 children in France in 1706, and her father was the principal secretary and introducer of ambassadors to King Louis XIV, part of that empire. She was educated, but we don't know a lot about her education. She was not a public figure at the time. Her father apparently recognized that she was brilliant and arranged for her to talk about astronomy with one of the leading French astronomers when she was 10 years old. Her mother was brought up in a convent, as was the tradition for many French women in those days. And there are indications that her mother approved of her early education, but actually encouraged her to question stated fact. In either case, that encouragement would have been unusual for young women of their time and status. Her father arranged for her to be trained in horseback riding, fencing, and a lot of other physical activities. And as she grew older, he brought tutors to the house, and we don't know who those tutors were particularly. But by the age of 12, she was fluent in Latin, Italian, Greek, and German. She was later to publish translations into French of Greek and Latin plays and philosophy. She was educated in mathematics, literature, and science. Her mother was so horrified at the pace at which she was learning, she attempted to actually put her in a convent. But her father resisted. And as a teenager, when she was short of money for books, she used her mathematical skills to devise what were apparently highly successful strategies for gambling. So in 1725, she married the Marquis Florent Claude du Châtelet-Lamont, and that conferred her the title of the Marquise de Châtelet. It was an arranged wedding. And as a wedding gift, the husband was made governor of Semur and Auxerre in Burgundy, and they moved there when she was 19. Her husband was 34. They had 3 children. In 1733, at the age of 26, with 3 children, she resumed her study of mathematics. And this time she was tutored by Maupertuis, who was a major French mathematician, a member of the French Academy of Sciences. And he had been educated by Bernoulli and Euler and others, and she had the world of mathematics at her fingertips. Voltaire says that they met in 1729 when he was back in France after a long exile in London, but nobody knows for sure. But it was after her 3rd child when she re-entered society. She invited Voltaire to live in her country home in northeastern France. That's whoops. Oh, can't do that. Sorry about that. And they became lovers and partners. They worked together, and to judge from Voltaire's letters to friends and their commentaries on each other's work, they lived together with a great deal of love and respect. She began an affair with a French poet in 1748 and became pregnant. And in a letter to a friend, she confided her fears that she would not survive her pregnancy, and she did not. She died from a pulmonary embolism at the age of 42. But before she died, she completed her outstanding achievement, total translation into French of the Principia Mathematica, including her derivation of the notion of conservation of energy and other things that were not explicit in Newton's work, but implicit. Conservation of energy is a powerful physical result, and Du Châtelet is the person who's responsible for it. And even today, her translation of the Principia is the standard translation of the work into French. Now, a little side story to that. I took French in college, 2 years, like many of you did, and I went to graduate school. And because I'd had 2 years of college French, I had a waiver from the French requirement for one of the 2 language requirements for my degree, my doctoral degree. But somewhere in about the 3rd year of my graduate study, I got a note from the registrar saying that, oh, we're real sorry, but we have lost all of your academic records. And the upshot of that was that I had to take a French exam. Well, they had changed then to standardized tests, but the previous examinations had been go to the office of a professor of French, and they'll take a book and hand it to you, and you translate. So I went to the designated office because I was sort of grandfathered into that way of doing it. And he pulled a book off the shelf, and it was Du Châtelet's translation, Voltaire of the Principia, which I had not read, did not know existed, but I knew the physics in it. So I could actually do some of the French, but it was just a gift in terms of not having to worry about vocabulary and other things. And after about a page, he says, "That's enough of that," and took it and signed my sheet, and I was gone. But that's the only time I've ever seen that book in actual print. So, what do we have? Well, I saw a slide that I can't go back to easily. I had summarized that what Newton had done, and this is important to realize about almost any of the people I'm going to talk about, is that he had taken a sort of hodgepodge of seemingly unrelated ideas and notions and guesses and synthesized them into one worldview that provided the springboard, one of the major springboards for the Enlightenment. I mean, Voltaire was arguably the first driver of Enlightenment thought in France and perhaps throughout Europe. But this book, this synthesis, this power of being able to predict nature, to understand nature, did that. And for that reason, there are statues of Newton, which you got a glimpse of at Cambridge. There's an incredible memorial at his burial site in Westminster Abbey. Voltaire wrote that at his burial, he had everything present for the burial of a king, except the king. I mean, that's the esteem at which Newton was held when he was laid to rest. So, with that, I'll stop and answer any questions you might have, or try to answer them. There should be one at least that I skipped over totally. If you don't answer, don't ask it, I'll ask it. Everybody's just sort of numb, huh?
Did you really see the apple fall off the tree?
There's no evidence whatever for that. But there are lots of apples in England, and sitting in a farm for 2 years thinking about, physics, I wouldn't be surprised if he didn't think it. It certainly could be true. Clearly, the way he approached it was consistent with the notion of getting the idea that there might be some link between the moon falling and the apple falling, or anything falling. But yeah, but there's no. A lot of Newton's life, all his life, he kept a journal. I mean, there's a statement in there when he was he was living with his stepfather, his stepfather had died and his mother was back in the house, that he wrote in his journal that he threatened to, I guess the father is still alive. He said, I wrote that I threatened to kill both of them and burn the house down around them. He had a temper. I didn't get into that very much, but he was not necessarily a pleasant person to be around. He was a genuine introvert. Yes? No. No, so far as I know, he never really even had a very close friend. I mean, he had people he corresponded with, but it was almost sad in a way. He was clearly well respected at Cambridge, not just for his scholarship. There was a point at which I don't know that I get this right, but I think it was King Charles II ordered Cambridge to give a degree to a Benedictine monk who had not passed the exams or taken the oaths of office that were required for to be given a degree, and whoever was in charge of making that decision demurred and was punished. And Newton spoke out very strongly, and actually was quite an activist in opposing. He was taking a real risk. But by the time all of this filtered up to the top, I think Charles II was no longer the regency who was in a position to make that decision. I think that William and Mary had become the rulers by then. But he was very highly respected for his stand against that and against certain aspects of the church generally, in addition to it. So, well, it came right after James II, I think, Bundy, whoever came in right after James II. But yeah, you're right. I don't have that. I didn't look up that particular thing. But I do know that there was a series of fairly dangerous comments that he made and public appearances that he made during that time standing up for the university and its prerogatives. He could be very. He wasn't like Galileo in the sense that Galileo could write this polemical prose to poke at people. Newton just got into almost violent confrontations, especially with Hooke and Leibniz. They were verbal, written, not physical confrontations over the prior, who was prior and deserved credit for the discoveries. But like with Halley, when people would ask him questions, he was always willing to answer them if he had the answers. He took a great deal of time to I guess, reconstruct what he had done earlier in terms of orbit calculations so that he could answer Halley's question. I thought you might ask me, what is gravity? Yeah. Yes, sir.
And maybe this edges on that, I'm not sure. Newton expressed his formula of mass and force. The force had to be greater, correct? To move.
Oh, well, it's more complicated than that. If you're going to move something on the ground, you have a frictional force you have to overcome, and the force has to be greater than that to make it move.
That's the key word.
Yeah.
The word I'm looking for.
Yeah.
Friction.
Yeah.
Okay.
And one of the reasons why I don't get too excited about the difference in the wording of the first law. Galileo surmised that if it was able to imagine a world in which there wasn't any friction, and which if something were sliding along a thing, there would be nothing to stop it. And so it would just keep on sliding it without any change. So, but we don't live in a world in which there are frictionless surfaces. They're close, but we don't have any that are truly without any friction at all, unfortunately, because you have to do work to overcome friction, and that costs energy and effort. Newton, one of the great quotes from Newton was about gravity. He did not like hypotheses. He thought that hypotheses were just guesses that didn't have anything to bear them out. And so he was ruminating in the Principia about the nature of gravity. He says, I make no hypotheses. In other words, I don't know. And I think that's the current state of the world when it comes to gravity. We really don't know. We could describe it. It's just like, it's not quite like time. And time and mass and distance we define operationally. Time is what a clock measures, and space is what a ruler measures. And then you just have to define what's a clock and what's a ruler. But gravity is something else, and it is a very, very interesting topic in and of itself. Yeah. Yeah, he said. He talked about what God is saying. It's called action at a distance. It's somehow the Earth reaches out and grabs the moon and pulls it, and somehow the sun reaches out across empty space and pulls us, and we pull on it. We'll have a better way to express that when we talk about electromagnetism. Probably after Christmas. I forget how these lectures are scheduled, but it's still, even with a better way to describe it, you still don't know exactly what it is, and yet it is. We're so familiar with it, we don't even think about it as a force. We know that. Yeah. But these are, these things that make a difference, and Newton started the scientific revolution in earnest. Within the next 100 years, enormous changes occurred in our understanding of the natural world. So I don't think he would have been a person I want to have dinner with particularly, but I would have loved to have heard one of his lectures on anything. As a fellow or a member of the faculty at Trinity, he was obliged to give lectures. Cliff, what was Trinity or Oxford like in the 17th century?
Newton is part of a minority. Most students at both of the universities spent most of their time drinking, gambling, and chasing loose women.
Yes.
With some success. There were, let's see, in Oxford in the mid-18th century, when Halley was there were at least, I think, 358 pubs.
Yeah.
Same thing in the 17th century, but they were not there to study. You were supposed to, at the end of your college, well, if you were wealthy enough, you would take a servant with you, and they would do all of the work. And they would get the education. And at the very end, you had to give a lecture. It was called a wall lecture, and it was given in Latin. And it's called a wall lecture because that's the only person who's there to hear it. It's the wall. And not the wall as in Midsummer Night's Dream. But the universities were not really cleaned up until the 1870s.
Yeah.
So you went to have a good time.
And you know, maybe certainly the university in the 18th century, maybe. Yeah. It was a very different life, and the whole structure. I mean, you studied pretty much on your own, and you attended lectures if you wanted, and you took the exam maybe to show that you learned something. So I don't know how many people attended his lectures. I know there are. I was not able to find any record of that in any of his biographies. So I'm guessing he was probably not the most popular lecturer at the university. Yes.
In another field, when you're doing transportation demand analysis between two cities, we use what's called the gravity model, which is exactly it works out very closely if you assume the population of each city is like the mass in Newton's formulas. And then the demand turns out to be inversely proportional to the distance between the two cities. And so it's called the gravity model when you use it.
Yeah. I should have made one other little technical point. When in this gravity law, every particle, every object attracts every other object. So if you think about the attraction between, say, the Earth and the Moon, here's a little piece of Earth, and up here's a little piece of Moon, and they attract each other with that force. But here's another piece of Earth, and here's another piece of Moon, and here's another piece of Earth, and here's another piece of Moon. And somehow you have to figure out a way to add all of those things up. And figuring out how to do that was the impetus for the invention of the integral calculus, for those of you who've taken calculus. He had to solve that problem mathematically before he could convince himself that it was as if the mass of the Moon were right here at this point and the mass of the Earth were right here at this point, and you could use that formula. And that's a formidable problem for students to consider these days, even if they know the mathematics. It is not trivial.
That's why it's called the center of gravity.
Yeah. Yep. Yes.
One
Thanks. Yeah.
A pound with 100 pennies instead of one with 280. And the British eventually adopted Newton's suggestion 300 years later. We don't rush these things.
Yes. Okay, well, thank you all. Our next one will involve one person you know well, or at least think you know well, and that's Benjamin Franklin, who you don't think of as a scientist, and an American backwoodsman whom you've never heard of. So it'll be a different talk. So thank you again. I appreciate your patience.